Good evening, students. The second unit is about the controller modes and tuning. Okay, so in the first unit, we have been discussed about the process. Okay, so we have discussed the level process and the temperature process. Okay, so for the same kind of process, let us see how we are tuning the controller. Okay, so the content in the second unit is about the first order, second order system, followed by the different modes of controller modes like discontinuous mode, continuous mode, okay, and composite mode. Okay, so here you can see the multi-position floating action, and if you take a composite mode PI, PD and PID, and let us see the selection criteria for controller, the need for controller tuning methods. Okay, so we will be exploring about the different tuning methods and the process identification for controller tuning. So first, let us see what is a first order system. Okay, so first order system is one in which the output is modeled by a first order differential equation. Okay, so a system in which the output is modeled by a first order differential equation, you call that as a first order system. Okay, so you may okay, the first order differential equation. Okay, so let us take the input as f of t and the output as y of t. So here you can see that you have a naught into y of t plus a1 into dy by dt. If it is having a first order derivative, okay, which is equal to b into f of t. Okay, so if it is having a first order derivative, we call that as a first order system. Okay, and here a1 a naught b are the coefficients associated with the input and output function. Okay, so here the input function is represented as f of t, output is represented as y of t. Okay, so to define the system, we have to derive the transfer function, and I hope already we are familiar with this. What is the transfer function of system? It is a ratio of Laplace transform of output to Laplace transform of input. So here, here the output you have, it is associated with the coefficient a naught, so divide by a naught on both sides. Okay, so you will get a1 by a naught into dy by dt plus y of t is equal to b by a naught into f of t. Okay, so here it is treated that a1 by a naught as tau p, b by a naught as kp. Okay, so when you simplify this equation, the first order differential equation, you will get tau p into dy by dt plus k plus y is equal to kp into f of t. Okay, so when you take a Laplace transform on both sides, you will get y of s by f of s is nothing but kp divided by tau ps plus 1. This is a first order process with a transfer function, and it is also called as a first order lag or linear lag or exponential transfer lag. Okay, so now let us see how the first order response will be. Okay, so here the process is modeled as a first order process because it is characterized by the capacity to store the material, energy or momentum, and the resistance associated with the flow of mass, energy or momentum in reaching the capacity. Thus, the dynamic response of the tank that has a capacity to store the liquid can be modeled as a first order process. Okay, so the resistance is associated with a valve, pump and pipes that can be attached to the inflowing or outflowing liquid. Okay, and in the first chapter we have been discussed about the level process and temperature process, and this process can be modeled as a first order process. Coming to the response. Okay, so when you want to learn about the dynamics of process, we need to obtain the time response of the process. Okay, so you may ask, what is the time response of process? When the process is excited with a step input, you will get the step response. It is one type of time response of the first order process. Okay, so let us take y of s by f of s is equal to kp divided by tau p s plus 1. Okay, so here y of s is equal to kp by tau p s plus 1 into f of s, where f of s is nothing but the step function which is represented as 1 by s. Okay, so it is kp divided by s into tau p s plus 1. Okay, so we want to obtain what is y of t. To obtain y of t, we need to take an inverse Laplace transform. For obtaining the inverse Laplace transform, we need to take the partial fraction expansion. So you can represent that as a by s plus b by tau p s plus 1. So we are computing the value of a and b, and substituting the same in this equation, and once taking the inverse Laplace transform, we will get kp into 1 minus e power minus t by tau p. Okay, so this leads to the exponential transfer lag. Okay, and if you see the response of this first order system, you can see that x-axis as a time and y-axis as amplitude, and when you give a step input you will get a step response. Okay, and its magnitude will be represented as y of t by k a into kp. Okay, and similarly if you take a second order process similar to a first order process which is governed by a second order differential equation, you can see that you will have a second order differential equation having second order derivative, that is t square y by dt square plus a1 into dy by dt plus a0 into y is equal to b into f of t. Okay, so when you divide this equation by a naught, so you will get a2 by a naught, a1 by a naught plus y of t is equal to b into f of t. When you simplify this, you will get tau square d square y by dt square plus 2 zeta tau into dy by dt plus y is equal to kp into f of t, where tau is a natural period of oscillation, zeta is a damping factor, and kp is a steady state gain value. Okay, so from this you can obtain what is the Laplace transform of output to Laplace transform of input, which can be represented as kp divided by tau square s square plus 2 zeta tau s plus 1. Okay, so this is the standard second order transfer function. Okay, so here y of s, to obtain the time response, once again you will give the forcing input as f of s as 1 by s, so you will get kp divided by s into tau square s square plus 2 zeta tau s plus 1. So you will get a two poles of the system, and for that based on the poles you can classify the system as three categories: over damped, critically damped, and under damped. Okay, so if a poles are are not real and unequal, you classify that as over damped system. If the poles are equal, you classify that as a critically damped, and if the poles are unequal and complex conjugate, you call that as sorry, it is a complex conjugate, equal and complex conjugate, you call that as a under damped system. Okay, similar to which you have explored in the linear and digital control system, you have to obtain the time response of the system by considering the poles as as unequal and distinct. Okay, unequal and distinct, so you will get kp into 1 minus e power minus zeta t by tau into cos h of square root of zeta square minus 1 into t by tau plus zeta by square root of theta square minus 1 into sin h of zeta square minus 1 into t by tau. Okay, so it is called as a overdamped response. Okay, and similarly you take a underdamped and critically damped. So for critically damped you will get y of t is equal to kp into 1 minus 1 plus t by tau into e power minus t by tau, and for underdamped response y of t is equal to kp into 1 minus 1 by square root of 1 minus zeta square into e power minus zeta t by tau into sine of omega t plus 5. Okay, so this is for the overtime, and similarly the response of the system, you can see this is an underdamped system, the response, and you have a critically damped and overdamped response. Okay, so from this one can arrive the performance by computing the value of a b c etc, right? So you can see you can compute the overshoot, decay ratio, period of oscillation. These are some of the characteristics of second order process: natural period of oscillation, response time, and rise time. And you can treat this second order system as a the multi-capacity storage tank. Say for example, interacting or non-interacting system can be treated as a second order system because it is having a two storage tanks connected in this fashion. So you can treat this as a second order system. Okay, thank you students.